So Jonathan Feng is a professor of physics and astronomy from the University of California at Irvine. He is, and I have to use my cheat sheet here, the list is long. He is a member of the Aspen Center for Physics. He's also an officer, which I think at the Aspen Center for Physics, which probably means I should have saluted him when he walks in. He's a fellow of the American Physical Society and a fellow of the American Association for the Advancement of Science. He's a Guggenheim Fellow, a Simons Fellow, and in my opinion, in general, a very fine fellow. He has degrees from both of the Cambridges, the one in Boston and the one in the UK, where I also attended. And he got his PhD from Stanford University. He was a Miller Fellow at Berkeley, a Fellow at the Institute for Advanced Study in Princeton, and then a Research Fellow at MIT before ending up where he is now at Irvine. Jonathan's work has had enormous impact on many aspects of theoretical physics. The list is long. He's worked on theoretical particle physics, astrophysics, and cosmology, and the range of ideas he's worked on is large. He's worked on collider physics, cosmic rays, supersymmetry, extra dimensions, but perhaps what he's best well known for is his work on dark matter and helping us to understand the nature of dark matter, this strange particle that makes up 25% of the universe and is there's 5 times more of it than there are of the particles that make up you and I. And despite all these great accolades in theoretical physics that I've just told you about, today he's going to tell us about a new chapter in his career. There's some work he's doing motivating and help design experimental programs to maybe shed light on what is dark matter. And as you see from his title, these experimental programs are faster, smaller, and perhaps most importantly, cheaper than some of the alternatives out there. And so please join me in welcoming Jonathan Feng, who's going to tell us how to discover the universe on a shoestring budget.
Okay, so thank you very much for that very kind introduction. It's a pleasure to be here. I actually gave this Pagels lecture 8 years ago over in Pepke Auditorium. I don't know if any of you remember when it was over there sometimes. Some of you might have been there. And I also distinctly remember staying after the lecture for like 45 minutes talking to people. So no pressure if you don't want to ask questions, but it's a fantastic forum, and I'm very happy to be able to talk to you today. Okay, so this is about experiments and ideas that have come up in recent years. But first I want to start out by just talking about this first phrase, discovering the universe. What does that mean? So the outline will be discovering the universe, that's part one. Then I'll talk a bit about traditional experiments, which are fairly big experiments, and they go by the name of big science sometimes. I'll tell you a bit about what big science means in our field. And then I'll talk about new experiments, where their goal is, in many cases, to be faster, smaller, and cheaper than the traditional experiments. This doesn't mean that they are fast, small, or cheap, but it does mean that they're supposed to be relatively fast, small, and cheap, and you'll see what I mean by that. Okay, so let's go ahead and get going. Part one, discovering the universe. So let me ask you, and this is not a rhetorical question, okay? I'm really asking you, if you lived in early times, long time ago, caveman sort of times, how would you begin to map out the universe? How would you begin to discover the universe? What would you do? Look at the sky. Okay, that is a great answer. That is exactly what I think you should do. And so you would look up, and you would see something like this. If we turn the lights down, you would see lots of little dots. And more than that, you would see sort of a haze running through there. And, with your mind, you would start wondering what those things are, and why is one band in the sky maybe a little bit brighter than the others. So this is something that's been going on since people have existed, since the dawn of time. And there's been fascinating developments, of course, every 100 years and so. But basically, if I were to try to summarize what we've learned since prehistory till now, we've kind of got the universe as observed in that way, looking at the sky, sorted into sort of 3 categories. So the first is something that we all learn about when we're in school. There's the solar system. So this is a picture of the solar system, which is not quite to scale. You see the sun here, and if all these planets were actually that close, they would all burn up and we'd be all dead by now. But this gets all of the, I guess, 8 now planets on the screen. And so here's Earth, and then as we go out, Saturn, etc. Now, if we look farther out, we realize that this solar system, which is so precious and wonderful to us, is not all that unique. In fact, this sun here is actually just a star. And if you look here, that sun is one of these little tiny dots here that makes up a much bigger object called a galaxy. And we are just sort of, hanging out here in the suburbs of this galaxy, not even close to the center, not special at all, and there's our sun. And that picture is then much bigger. You've zoomed out to about 10 to the 17 meters. But that actually is not as big as we know. In fact, we know now that galaxies are sort of sorted into things called clusters of galaxies. So just as on this picture, every dot of light is a star, on that far one over there, every dot of light is actually a galaxy. And so we see clusters of galaxies, which are sort of the biggest sort of organized objects in the universe. And that takes us out to 10 to the 23 meters. Okay, so if you just looked at this, you might say, well, we've done a pretty good job figuring out what's in the universe. And so what is there to discover? What's so interesting? What else is there that could possibly sort of surprise us? We've got a nice picture of things from our local neighborhood, our solar system, all the way out to almost unimaginable distances. So what happens is that, of course, we don't just look for things as static objects. We look and see how they move in things, okay? And so let's go back to the galaxy that I showed you there. This is sort of a spiral galaxy. And as you might know, spiral galaxies rotate. They have what are called arms, and they rotate on each other, okay? And so we observe these rotations, not exactly like this, but let me just cheat a little bit to get to the point. And what I want you to do is take a look at these two galaxies and see if you can tell me what's the difference in when they start rotating. Okay.
Right has much more fixed, I guess, rotation, but actually not rotation, but much more fixed, I guess, spin.
Fixed spin. So the one on the right, you say? This one over here?
Yes.
Okay. So sort of, let's see, what do you mean fixed spin? Like the inner ones compared to the outer ones? Or
In other words, the outer portions are moving faster relative to the inner portions compared to the one on the left.
Yeah. Okay.
The ones on the left are moving maybe more ballistically, the way we would imagine that in orbit around the around the sun kind of thing. More ballistic orbits. The other ones looks like there could be something on the outside that would be causing that to be significantly, slowed down in the center or sped up on the
edge.
Visible light spectrum.
Okay. So let's see, are there any other opinions, any other answers?
The one on the right seems to move as if it's a solid one object, even though we know it's not. Where this one moves more like a gas, where the spinning inside and much more lag on the outside.
Yeah, very good.
Like the other gentleman said.
Right, but in interesting and different way of looking at it. Good. Any others? Maybe one last one here.
Looks like the one on the right is rotating faster.
Okay, but not necessarily all of it is rotating faster, right? Let's just take one more look. I think we got time for this. If you look at the insides, they're kind of rotating about the same speed, right? But the outside, that's where there's a real difference. You see, these guys are very slow and lazy, whereas these guys are kind of moving along, right? Okay, so hopefully you guys can see that. So astronomers, astrophysicists, look at these sort of things. Now, they don't actually see galaxies do that. That would, in real time, take 100 million years. But they see velocities of individual stars, and they can therefore sort of extrapolate to these sort of motions. Now, when they do that, what's interesting is that the left is actually what we would expect, and the right is actually what we see. Okay? Now, what does that mean? What do you mean what we expect? Well, we can look at this galaxy and we can figure out how much matter there is in here, how many stars, how dense they are, and things like that. And from that, we can figure out how much gravitational pull is acting on all these stars, but in particular the ones on the outside. And from that, the fact that they go around in this orbit means that their sort of rotational motion is balancing the gravitational pull, and we can predict how fast they ought to be going. And the prediction is this. But that's not what we observe. What we observe is actually this, and this is actually what's called a rotation curve. We actually observe that stars are going at velocities almost independent of how far they are from the center, which is really weird. So this is pretty interesting. Stars on the outskirts rotate faster than expected given the visible matter. Something else has to be pulling them toward the center. So in this case, they're going so fast. Something else must be pulling them in. Otherwise, they're so fast that they should have just gone off to infinity. That galaxy should have basically just blown apart and not been a galaxy anymore. Okay, so all of a sudden, this idea that our universe is pretty well understood pretty much goes bye-bye, and we realize there's a whole bunch of things we don't actually understand. With that sort of rotation curve thing, which you guys could even see with your own eyes, and a lot of other evidence, it's apparent now that actually the stars we see are just islands in an ocean of invisible, what's called dark matter. So this thing, which we thought was our galaxy, is the whole picture. No, not really. Actually, the accurate picture is this. This is the sort of spiral galaxy that we see, but it's embedded in this huge ocean of what's called dark matter, some other stuff that actually is pulling and keeping this galaxy together. In fact, we've of course become more quantitative than that. The surprising result is that there is actually 5 times more of this dark matter stuff than normal matter. Okay, so it's actually, we, normal matter, are the minority in this universe. We are a small sort of smudge on the universe. And the other thing that's important to get straight is this dark matter is not out there. Okay, it's not this sort of space science thing that we could ignore. This dark matter is out here, sure, but it's also all over this galaxy, spread fairly uniformly throughout the galaxy. And in fact, there was dark matter particles passing through this room as we speak, and passing through your body. If you take some of the most popular theories, about 1 trillion of them have passed through your body since we started talking. Okay? So this is not a sort of, oh, let's let someone else worry about this problem. This is a problem for us right here, right now. Now, that's not the only thing we've learned, that there's dark matter. We actually have a lot of things. I, of course, can't summarize all this astrophysical data. It's just been a huge, amazing development in the last 20, 30 years. But this is the sort of the summary plot. Summary plot is that we now have an overall picture of the universe. The universe, if we think of that as 100% of this pie, has 5% are atoms. Basically, all these things that we learn about in school, every kind of chemical element, if we add all those up, they form this little slice of the pie, 5%. The dark matter, which I just talked about, is actually much more prevalent, 27%. And then there's some weirder stuff even, which is called dark energy, which actually makes up the bulk of this, which is 68%. Okay, but we now have an overall picture of the universe, weird as it is. And so what I want to tell you is that, we know a lot about a little. We know a lot about this normal matter slice, but we know little about a lot. Namely, this other 95%, we've kind of got names for it, but we don't really know much about it, and we certainly don't have a deep understanding of what it is. And so that's what I mean when I say we need to discover the universe. We have 95% of the universe where we just have no real idea what that stuff is. Okay, so let me try to, if this is the first time you've heard of this, this might be sort of amazing. Let me try to give you a historical precedent to sort of set this in some context. Instead of asking about the universe, we could have asked about the Earth. So if you lived in early times, how would you begin to map out the Earth? Well, especially around here, what you'd probably do is go up a mountain and kind of look around, right? That would be a way of getting a better view than just sitting right here looking around. If you go higher, you can see more. and you try to map out, what's going on around here. And you'd get, a much better, maybe many miles view than you would get sitting on some low place. But of course, that's not really giving you a global view of the Earth. That's not mapping out anything except for, the region around Aspen, Colorado in this case. But just like in the universe case, there was a brilliant person who found a way to do this more globally. And this is a person named Eratosthenes, who's just an absolutely amazing person. Anyone here should go back to Google and find out all about him. He did the Eratosthenes sieve to find prime numbers. He invented the leap year. He was the librarian for the library in Alexandria. The other thing he did, kind of in his spare time, was he measured the size of the Earth in 200 BC. Amazing. Just, that's a long time ago. What he said is, okay, here's the Earth. And I think he knew it was not flat already. And there's the sun. And the sun shines rays at us. And they're parallel, because the sun's really far away, so the rays are pretty much coming parallel at us. And he was in Syene, this place that at certain times of the year, he had actually a well, and he could look and see that the sun rays went all the way down this deep well, which meant that the sun was directly overhead. And so this sun ray was pointing down deep into a well. And so then what he did is he sent out an assistant to Alexandria. This assistant, what we'd call them now, is a graduate student. They trekked up there on a camel or something. And he said, when we have this special day when we can see the sun is directly overhead, stick a stick, vertically and see how big that shadow is. And so this is what this graduate student did. And by measuring how long that shadow was, you can figure out basically how curved the Earth is, right? So if the Earth is really small, then if you go 400 or whatever distance it was, you get a big shadow. If the Earth was huge, then this would be almost flat and you get a small shadow. And this is a really neat thing you can do. But he did this in 200 BC, and he got an answer for how big the Earth was. And so he got an answer that was actually thought to be unbelievably large. Many people didn't believe it. Apparently, Christopher Columbus didn't believe it. If he had believed it, he would have realized he wasn't in India. He was actually in the Virgin Islands or wherever he was. People didn't believe it for hundreds of years. But we actually now know that he was right up to about a 10% error. It's a really amazing result. Okay, so why is this a historical precedent? Well, basically, his result gave an overall picture of the Earth, right? In some ways, he kind of mapped the Earth. He figured out overall what it kind of looks like, how big it is. But it's hardly a complete understanding of the Earth, right? We wouldn't call his measurement, oh, now we know the Earth like we know it now, like with Google Earth. What was required to actually make this a very precise map, or a more precise map, was what's called the age of exploration. And so, many centuries later, people got up the technological know-how to build ships and go traveling around. And if you were in 5th grade, you would actually remember all these people and what they did. But I don't think there are any 5th graders here, so we'll just have to remember that we knew that once. But that started making the map of the Earth filled in, okay? And so what my point is that for the universe, we are now kind of where Eratosthenes was. We have a complete picture kind of the universe, but as for details, we really have no clue. And so we are now starting on our own age of exploration. It's a really interesting time to be alive in science right now. Okay, are there any questions? That was part 1. Yes?
When you say that dark energy is 68% of the universe, and dark matter is 27%, percentage of what? I mean, is this volume or is this?
Good. So it's actually energy density, or you can think of it, at least in the dark matter case, as mass density. So sort of if you took sort of an average volume in the universe, which is hard to find, but if you took one, you would find 5 times more mass of dark matter than you would of normal matter in that volume. So that's how we account for it.
How do you compare the energy to the mass?
Well, okay, in a second I'll talk about this E equals mc squared, but that's basically how we convert energy and mass measurements back and forth. Good, yes?
About a month ago, there was an article in Scientific American raising a question about whether or not there really is dark matter, saying that the other aspect of that equation is the correctness of general relativity, and saying that maybe general relativity isn't right, and maybe there is not dark matter. Can you comment on that?
Yes, I certainly can. This is a very interesting question on galactic scales. And in fact, if we just took the galactic rotation curves I showed you, this would be a fascinating question of whether dark matter is the only explanation of that or not. What I didn't show you was like the 9 other pieces of evidence that show that there is dark matter in the universe. And it turns out to be very, very difficult to modify general relativity to account for all those. And so even I would say even the most vocal proponents, opponents of dark matter who argue that it's just a modification of gravity, and I talk to these people and we are on panels and we debate each other, even they at this point would recognize that to explain the other pieces of evidence, you're going to need dark matter. And so, maybe dark matter doesn't fix all of the the galactical rotation curves, but it's going to be needed for other things like cosmic microwave background. Good. Yes, one last one.
The same question for dark energy. Is there an alternative explanation for dark energy along the same lines?
Well, not really. Dark energy is a very large encompassing term, and it includes things like vacuum energy, quintessence, a whole bunch of other ideas. So if I call it, if I allow it to be that big of an umbrella, there's not really an alternative, I would say. But it's incredibly thorny what that actually means, that dark energy. Okay, last one. Yeah.
Is it an assumption that dark matter obeys the identical equation as regular matter of same units?
Well, so it obeys the same sort of gravitational pull. Oh, good. The question is there an assumption in all this discussion that dark matter obeys the same, that's kind of, yeah, it obeys general relativity, that if it has a mass, it gets pulled the same way normal matter does. And yes, there is an assumption of that. Yeah. Okay, great. So we've talked about what I mean by discovering the universe, and I hope you see that there's a lot of interesting questions out there. So what are we going to do about it? So part 2, traditional experiments, big science. So we want to figure out what this stuff is. So how do we go about it? Well, if I use my nice Earth historical precedent analogy, in the case of the Earth, we needed to prepare ships that could take us into the unknown. And you didn't know where you were going, and so there was some question, but you knew you wanted probably pretty big ships and that had a lot of food in them, et cetera, like that. For the universe, we need to prepare experiments that can find the unknown. But if it's unknown, how do we go about preparing experiments to find it? That's a very good question, right? The answer can be traced back, I think, to 2 giants of physics. And if we go through what they contributed and what's happened since their work, it leads to what we would now call big science. So what I want to do is try to take you through those last 110 years of activity, so you can see how this has developed into big science. So who's one of these giants? Well, as usual, one of them is Albert Einstein. In 1905, Einstein discovered this famous equation, E equals mc squared, which says that mass can be converted to energy, and energy can be converted to mass. Okay? Now what that meant was that you can have processes, you can kind of think of them as chemical processes or just things that happen where you have, for example, 2 protons that smash together, so they have mass. Their mass is converted into energy, and then that energy can go back out and be sort of manifested as mass again, but not necessarily proton mass, but by some X mass, mass of some new particle X. Okay, so you start off with 2 protons, bring them together, they collide, and out come 2 new particles. This is an amazing thing, because what it's saying is that energy is a sort of universal translator, if I were to use like a Star Trek analogy. You know, Star Trek is always amazing. These guys, people can talk, and then there's 6 million languages, but somehow the other person can understand, right? In this case, energy is that universal translator. We can take known particles, like this P here stands for a proton, collide them, form this energy, and then that energy can turn back into particles that aren't protons, but can be other things, like some unknown particle X. And so what this means is that you can discover new particles without even really knowing what they are. You just smash together 2 protons and figure out what comes out here. It's not like you have a particular kind of particle that you would have to assemble like Legos. You'd have to know exactly what that particle is to do it, right? And that'd be very hard because we don't know what these particles are. Einstein's E equals mc squared tells you you don't have to know what these particles are. Just smash together 2 protons and see what comes out. Now, a couple of decades later, E.O. Lawrence did just that. So in the 1930s, he made what's called a cyclotron, which basically the idea was, okay, if this can happen, let's make particles go faster and faster, bring them to higher energies, and then smash them together and see what happens. Here's E.O. Lawrence. This is the first cyclotron he made, which you see can be handheld. It's about the size of your iPhone. And that was an amazing beginning. After a while, people realized, hey, if I make this a little bigger, I can accelerate particles to higher energies, I can make heavier particles, and I can discover and produce more and more particles. And basically, I mean, even in his own lifetime, this took off, and this was, you know, not the state of the art for very long. Very soon, these things got bigger and bigger and bigger, and it basically led to big science, this kind of idea that you have a lot of people working on big machines, and you can discover lots of things, in particular, many new particles in this way. So if I were to flash forward to now, what has this got for us? Well, now we know that the normal matter, atoms in the periodic table, is completely made out of just 3 kinds of particles. There's things that are called up and down quarks, U and D quarks, which bind together in various ways to form protons and neutrons. And then we have the electrons, which kind of go around the outside of the nucleus, which is this atomic model I think most of you know. But with these colliders, we've actually found many more particles. So these blue circled ones are all you would need to basically account for everything you see in this lecture hall. But we found, through colliders and also sometimes not colliders, a whole zoo of more particles. There's other quarks, funny names, charm top, strange bottom, more electron-like things, muons, taus, neutrinos, force-carrying particles. And the last one, which isn't even on here, is the Higgs particle, which was found in 2012, as probably many of you heard about. So we've actually extended the known particles with these colliders a lot. And so there's a whole bunch of new particles. But every single one of them, very quickly, I won't go through it here, but very quickly you can show that not a single one of them can be dark matter. They don't have the right properties. And so there's still got to be more particles out there that can be the dark matter. And the search goes on at bigger and bigger machines to sort of find these. Now, what kind of is the state of the art then? Well, the biggest, grandest realization of Lawrence's vision today is probably, you would call that the LHC in Geneva, the Large Hadron Collider. So, you know, this is the big version of E.O. Lawrence's thing that he was holding in his hand. This is, the red thing is the LHC, the Large Hadron Collider. It goes around the Swiss-French countryside. For scale, this is Lake Geneva. This is the Geneva airport. And this is huge, right? It's underground, a couple 100 meters, 100 meters. And it accelerates protons in one ring this way and in another one this way. So they're counter-rotating rings of protons, but it can get them going to 99.999999% the speed of light. So really fast. So that's the LHC, that's this collider. And then at various points along this collider are experiments, are detectors. So they're labeled with these yellow dots. Atlas, CMS, LHC-B, Alice are some of the big ones. And at those particular points, the counter-rotating proton beams are forced to collide with each other. And we do this thing where we collide two protons and look for what comes out and try to find something new, for example, maybe dark matter. So the LHC is huge. If we zoom in, so for example, to this atlas point and look there to see what we see, you see a detector, which is trying to very carefully monitor what comes out when two protons smash together at that point in the ring. Does anyone see a person in this photo? Okay, so this is a person right here. So this is like a 2-meter high person. And so that sets the scale. These are enormous detectors, giant building, 6-story building type detectors with lots of intricate components that all do various things to try to catch various properties of the particles that come out. Okay, so that is like a great example of big science now. So let me try to give you an example of how big is big science now. So you saw the sizes of these things. I would call that big. Okay, how about the time scale? How long does it take to mount an experiment or to create something like the LHC? Well, the LHC was conceived in the 1980s. It was constructed from 1998 to 2008, and then it's been running since 2008 with periodic shutdowns to upgrade and fix equipment. And it's envisioned to go on into the 2030s. So we're talking about, possibly a 50-year-long experiment from the time of conception to when you pull the plug and turn it off. How about the budget? The cost of constructing the LHC, that ring, and the various experiments, those detectors that are put along the ring, totaled up is about $10 billion. That's just to construct it, and then, of course, you need to operate it. Once you've got it built, you got to make sure it stays working and operate it. The annual operations budget of CERN, which is the host laboratory in Geneva, is about $1 billion per year. Now, whether you think that's a lot or not, that clearly depends on, okay, so some people, this is Aspen, so some people think this is cheap. In some sense, I agree with you. If you ask, what are people giving up to do this? This is, of course, a European Union project. People are giving up 1 coffee per year per EU citizen. And so the Director General of CERN, Fabiola Giannotti, who's Italian, says, yeah, and that's hardly any sacrifice for all those people in England and Norway because they have crappy coffee. So, Italians, yeah, that counts for a lot, but for up there, no sacrifice. But okay, anyway, that's one way to look at it. But it's $1 billion a year, and so that's not something you're going to just pull out of your pocket. How big are these collaborations? How many people does it take to do this? The number of physicists working on each experiment is large. So let me give you an example of that. This is a CMS, one of those detectors that I had on that map. This is a recent CMS author list. So they publish papers, and of course they have authors. And so this is the CMS author list. But this is the first page. If you look carefully, what this is doing is it's alphabetized by country. So we start with Armenians, Austrians, Belarus, Belgium, blah, blah, blah. We've only got to Brazil here. The author list continues. Now we've got China, more. This is all the same author list. And you see I got more and more tired of cutting and pasting this thing, so I just shove more of these and more of these onto this thing. Here's the final end of it. It's about 4,000 physicists from 200 institutions in 43 countries. That's what it takes to actually build that thing and make it work. Okay, now lest you think that that was an exception, I just pulled the most enormous example out of a hat. Well, it is probably one of the biggest ones, but there are other ones that are very big science too. Just give you some examples. This is an experiment called Ice Cube. It's in the Antarctic ice. So this is the ice surface up here, and then basically strings of detectors are dropped down by melting the water. And here's the Eiffel Tower for scale. Okay, so you see it's huge. And it's called Ice Cube because it's almost literally a cubic kilometer of detector in ice. And what's being done here is they're looking for neutrinos. They have a fantastic physics program. But one particular aspect is that dark matter, which is, as I mentioned, going all around us right now. Sometimes the dark matter particles can collide with each other and make neutrinos. And so the ice cube looks for those neutrinos. And if it found particular kinds of those neutrinos, it would be seen as evidence for dark matter colliding with each other. So that's another interesting probe, but another example of big science. There are also things that are actually called dark matter detectors. This is one of several famous examples. This one's called Xenon One Time. What's going on here is people are looking for this kind of process. So you have nuclei, which are sitting in some vat of liquid or something, or solid or something. And the dark matter, which is whizzing all around us, sometimes will come through and hit one of those nuclei and bounce off. Now, you can't ever see the dark matter because it's basically invisible, but you will see a nucleus, which is just sitting there minding its own business, all of a sudden recoil for no apparent reason. And that recoil can be taken as evidence of dark matter, if that were ever seen. As I mentioned to you, trillions of these things have been passing through your body since we started, so this is not going to be an easy experiment. These things don't interact very strongly. Right now, the state of the art is that these detectors are about 1 ton in size, so very large, and they're very carefully monitored so that they can see if one dark matter particle comes in and hits a nucleus in there once a year, they would be able to be sensitive to that. So that's the state of the art for these kind of detectors. But you need big detectors. Okay, so I've given you, there's many other experiments I would love to talk about, but I can't given the time. But each of these experiments, these big experiments, is really a testament to human ingenuity and what can happen when large groups of people have a very focused goal, people from different countries, different backgrounds, and work together. It's really an amazing achievement. They continue to gather data, all these ones I've mentioned to you, and anyone could announce a groundbreaking discovery at almost any time. So it's a very exciting time right now with all these large experiments running. That said, so far, none of them has discovered evidence for new particles. Some of them have been running longer than others, but at this current time, there is no compelling evidence for these new particles that we know to be out there. So in the absence of discovery from one of these guys, what other approaches are possible? What should physicists be doing in addition to encouraging and working on those big projects? Well, I found a very interesting quote, which is from Captain James Cook. Many of you know him. He went around the Pacific, was very unfortunately killed in Hawaii by some misunderstanding, I guess. But while he was setting off, he was apparently offered some giant ships for his Pacific voyages. And he replied, "If you plan to make a voyage of discovery, choose a ship of small draft." That means a ship that doesn't have too much under the water, because you can kind of get in and out, you can explore little rivers and things like this a lot better. So that's an interesting idea in the face of this big science. And what I want to tell you now is that a few small groups of physicists are now taking Captain Cook's advice to heart in the realm of physics. Okay, so that's the end of part 2. Any questions? Yes?
If we don't know what dark matter particles are, what makes us think that the collision of dark matter particles would produce neutrinos?
Well, that's a good question. So the question is, if we don't know what dark matter is, what makes us think it might produce, in collisions, neutrinos? And the answer is, there are some known models of dark matter which would do that, and there are some that won't. And so, you look, and if you don't see anything, you kind of exclude some set of models, but other ones which didn't predict there were any neutrinos in the first place, you didn't exclude them. And so it's really, it's tricky, because we don't know what this thing is that we're looking for. But because of what I mentioned about Einstein and Lorentz, there sort of is some feeling that by colliding particles, we should have some handle on a lot of these things. Yes?
You said that there were no evidence for new particles. What about Higgs?
So that's, old news now. So the Higgs is a found particle. We're all over that by now. Yeah, that's right. So 6 years is a long time in particle physics. very high expectations. So nuisance Higgs, yes. Yes?
A minute ago, when you talked about at the Large Hadron, the particles going at virtually the speed of light, 99.999. Is that the speed of one particle going clockwise, or is that relative to the other particle going counterclockwise?
That's each one relative to someone standing on the side of the ring. So yeah, each one.
One is going at virtually the speed of light. Why isn't their relative speed in excess of the speed of light, which we say we can't do?
Well, that's this amazing fact about special relativity. So just because one particle is coming at me, when I see them coming at the speed of light, the other one's coming this way at the speed of light, that doesn't mean when if I were sitting on this particle, I would see that one coming at me at 2 speeds of light. And that's because of the fact that Einstein showed us that time is actually changing. And so all your very logical, seemingly, ideas about how to add velocities doesn't quite work. Yeah. Yes?
So dark matter appears to be affected by gravity. Do we know if it's affected by electromagnetism?
So we have pretty strong reasons to think it's not affected by electromagnetism. And that's because effectively, if it is, that would mean that it shines and it wouldn't be dark. So if it has electromagnetic interactions, it couples to photons, it shines light, and then we would see it. So there's pretty strong bounds on it not having electromagnetic interactions, and also shouldn't have strong interactions. There's one other interaction called a weak interaction, which it could have. Yes, yes?
I also have a question about the speed of this particle. So you said it's 99.999 and so on. So it's almost the speed of light. What if collider was, let's say, 2 times bigger? Would it be possible to reach the speed of light or even to exceed it?
Yeah, you can never exceed it or reach it even. So you just get closer and closer. And one way you could kind of intuit this is that as it gets closer and closer, in some sense it gets heavier and heavier, so it gets harder and harder to make it go faster. That's sort of a heuristic way of understanding that. But yeah, you can't ever get to the speed of light with a massive particle. Okay, yes?
So, if dark matter is particulate in nature, then there might be a need for the Higgs boson particle to associate mass, and then from their gravity. But if it is not particulate in matter, or the way that it is in its essence, then what would the need for the Higgs boson particle be to explain the presence or the observed presence of gravity when, for instance, you're watching these galaxies? Why is there, I mean, if it's particulate, why would there not be a Higgs boson particle associated with that presumptive mass? Or if it doesn't have mass, how is gravity associated with something that's massless?
Yeah, okay, so you have, that's a whole series of interesting questions. The Higgs boson that we've discovered, we need it because it has to give mass to the particles we know about. Okay, so irrespective of dark matter, that Higgs boson is doing a very important job. Whether it also gives a little bit of mass to the dark matter, and whether it interacts with the dark matter is an open question right now. Whether the dark matter has its own Higgs boson, a dark Higgs boson, which gives it mass, is an open question at the moment. So there's a whole bunch of things we don't know, and people write down models and theories with all these various possibilities to try to motivate new ideas and new ways of looking for this stuff. Okay, maybe these last two, and then we'll go on. Yes.
Is there an assumption that the dark energy is interacting with the dark matter the way our energy reacts with our matter? Is that
So in everything I've talked about and we'll talk about, the dark energy is kind of set aside. So we're not assuming that it does anything particular with dark matter. Pretty much we're punting on that issue. Okay? Yeah. Sorry, one more question.
So when it interacts with a nucleus, does it change the structure of the nucleus at all?
Most times we assume not. Most of the times we call it an elastic interaction, and it just moves it, so it picks up a recoil velocity, but doesn't change the innards of it too much.
So you don't
Yeah.
expect that it causes any biologically relevant mutations, is that correct?
That's right, and in fact there's the whole story there actually, but yeah, we expect it to be very weakly interacting, and so it doesn't do that. Okay, great. So now let's go on to part 3, the last part of the talk, which is new experiments, which are faster, smaller, and cheaper, we hope. So to introduce this, I have to tell you this story about the lamppost, which is very prevalent in science. Many of you might have heard it, but for those of you who haven't, you might think it's funny. So there's a guy who was wandering around under a lamppost, a street light, and looking around on the ground, and a policeman comes over and says, "What are you doing?" And the guy says, "Oh, I'm looking for my car keys." So the policeman says, "Oh, okay, I'll help you." So he wanders around, and they're looking around together. After a few minutes, the policeman says, "Where exactly did you lose these car keys?" And the guy says, "Oh, I lost them over in the park." The policeman says, "Well, why are we looking for it under the lamppost?" And the guy says, "Well, the light's so much better over here." Okay. So if we're going to reevaluate where we're looking for things, one thing we might ask is simply, where would things be so that we could find them if they're there? Okay? In other words, let's stop kind of assuming we know where things are, but simply take a very pragmatic approach, which is, where can they be such that we could find them? Because if they're somewhere else, it doesn't really matter, we'll never find them. Okay? So you can then classify all these particles, which come in thousands of varieties, in this one plane, which of course oversimplifies, but it's a helpful plane. So this is a plane where on this axis there's the mass of this hypothetical new particle. And so this is light and this is heavy. And then on this axis is the interaction strength. So up here is things that interact very well with us, and down here is things that interact very weakly. Okay, so everyone get those two axes? Okay, so where could we be in this plane? Well, if we had very light particles, so on this side of this axis, that interacted very strongly up here, those would be really easy to find. And in fact, we've already discovered them. One of them would be the electron. It's very light, interacts very well with us. We would have seen that. Those things could not get away. We would have already discovered them. The opposite extreme, if they're very heavy down here, and they interact with us very weakly, then, okay, they might be there, but they're just impossible to discover. You're never going to find those. You'd have to build a collider that's way bigger than the LHC, and you'd have to run it for 1,000 years or something. That's just hopeless. So these are impossible to discover. So all the real action takes place on this axis in the middle here, where you have strongly interacting heavy particles and weakly interacting light particles. Now, if you ask, what is the legacy of E.O. Lawrence and collider physics these last almost 100 years, the idea has always been to continue pushing on to higher masses up here. And hopefully they're strongly interacting, or else you're down here, you won't see them. And so, in effect, the traditional target of big science has basically been these particles up here. But you see that there actually are other particles which we could discover if they were there. And so these have now attracted a lot of recent attention because we built these big things, we haven't seen anything. What else can we do? Well, maybe we can look for light particles, which are nevertheless very weakly interacting, and that's why we haven't seen them so far. Okay, so this has become a very active region to search for new particles in the last 5 or so years. So I want to tell you a bit about some of these. So remember, now we're looking for light particles, okay, not heavy ones. If you have light particles, it turns out there's a whole bunch of new ways to look for them. One of them is in nuclear experiments. So if you have light particles, we don't need giant colliders to produce them. In fact, we can look for them by kind of redoing 1960s era physics experiments, nuclear physics experiments, in a more precise way. I mean, obviously we have to do something different, or else people would have seen them before, but we can do them without huge resources, as I'll show you in a second. So for example, and this is not a random example, But for example, we can make lots of excited beryllium-8 nuclei. Okay, that's 4 protons, 4 neutrons. It's not that hard to make them. You take a proton, you smash them into a lithium foil, and out will sometimes pop a beryllium-8 nucleus. Okay? And what we can do is look to see what happens to them. They will decay, they will kind of fall apart, and see if they fall apart and make new particles while they're falling apart. This diagram here shows an example where this is falling apart and it makes a new particle X, X for sort of unknown, which then decays further to electrons and positrons. Now, why did I pick beryllium-8? There's lots of different nuclei you could have thought about. Well, there's an experiment called the Atomic experiment, which has been looking at beryllium-8 nuclei. And this is the detector of the Atomic 8 experiment. It sits in a room in Debrecen, Hungary, in the Atomic Nuclear Physics Lab. You know, you see this scale. This is the detector. The proton comes in, hits this lithium foil, and these are these little detectors. And here's the, desktop computer for scale. So this is, of course, a huge difference from what I showed you before, the Atlas detector, where you couldn't even find the person, right? But because we can now look for light particles, this actually has interesting things to say. In fact, very interesting. In 2016, this Atomic group reported evidence that beryllium-8 nuclei are indeed decaying to new particles X, which then further decay to electron and positron pairs. If they're right, this new particle they've discovered is only 1/50th the mass of the proton. So it's extremely light, but it's extremely weakly interacting, which is why no one saw it before. Just to give you an idea, it's, I showed you how big it was. It's very small. Here's the entire author list. I don't need 5 pages to show you the author list. This is them, okay? It's 10 of them or so. This is their data. I'll probably skip that, but it has very suggestive of a new particle. They've calculated that the probability that it's just a fluctuation in the background is 5.6 times 10 to the minus 12. In other words, you'd have to do this experiment 1 trillion times before you would expect this to just happen by accident. So this is pretty tantalizing. And it's either the first sign of a new particle, or it's some experimental error that's just leading to this bump. A lot of people have looked, tried to figure out what the error is. No one has figured it out. But of course, the whole point of the scientific method is we need to follow up and see if someone else can see it. So there are now follow-up experiments trying to reproduce this result, which will either confirm this revolutionary discovery or else we'll find that it's just wrong. Another way, if you're going to consider light new particles, is you can go back to dark matter detectors. So I think I told you, the way we look for dark matter is, one way is dark matter comes in, hits a nucleus, like sometimes a xenon atom, which then recoils. If dark matter is very light, that recoil is not going to be very big. The example I want to focus your attention on is the idea of a ping pong ball trying to cause a recoil in a bowling ball. If that ping pong ball comes in and hits that bowling ball, what's going to happen? The bowling ball is just going to sit there and the ping pong ball is going to shoot back, right? You're not going to get any recoil energy on that bowling ball. And so if you're looking for light dark matter, these experiments are really perfectly designed not to see what they're looking for. What you really want to do, or one thing you could do, is you could design a detector to look for these ping pong balls hitting ping pong balls. That is, hitting some known particle that's much lighter than a nucleus. And we know about one of those. Those are electrons. So here's shown a diagram where dark matter can hit a nucleus, but it can also hit one of these electrons that's orbiting around on the outside. And if the dark matter is light, this ping pong ball interaction will be far more promising for you to see a recoil in a ping pong ball. Now, because current detectors don't do that, most of them, they look for this, the bounds are extremely poor on light dark matter. And so even a very small detector that can look for electron recoils could actually find dark matter. So there's an experiment called the Sensei Experiment. Again, it's small. Here's the entire author list in their recent publication. And just a few months ago in 2018, they released data where they collected 0.019 gram days of data. So we're talking about a detector that's like 1 gram in weight. and running for like a few hours. Compare this to the other ones I showed you, which were ton size and running for years. Okay, so this is a completely different kind of experiment. Nevertheless, this small, tiny experiment achieved world-leading results because it was looking for a different thing, looking for light dark matter. And so this is a result they published. Here's the mass of the dark matter. Here's how strongly it interacts. All the other experiments basically ruled out regions that are in this sort of light blue region. But as you see, as it gets lighter and lighter, they get very, very poor in how much they can rule out. Basically, they're completely insensitive to very light dark matter, whereas Sensei is actually providing the world-leading bound with this thing that fits on your thumbnail. The cost is $1 million for this whole thing. It was so small that you don't need giant labs, giant governmental agencies to support it. In fact, largely it was supported by a private foundation, the Heising-Simons Foundation, which is a very interesting new development. And the time from the funding starting to the result they just published was about a year. So we're not talking 50 years or 30 years, we're talking 1 year. Okay, last, and I just saw the time, so let me try to get through this quick, but this is my baby, so I have to talk about it. Another thing you can do is actually revisit the LHC and look for light particles. Okay, so we don't even have to build anything new. Let's just go back to the LHC and look for light particles instead of the heavy ones. It turns out if they're light, they might have escaped traditional searches. So here's an example. At the LHC, light particles are dominantly produced parallel to the beam, not perpendicular to it. So here's a diagram. So the proton beams come in from each direction, and then they smash together in the middle here. And what is expected for most new particles is that they kind of come off perpendicular. And so you have this incredible infrastructure of detector all around the perpendicular direction looking for these new particles. But if they're light particles, they dominantly do what's in the red here. They just go up and down that beam direction. They go parallel to the beam. What does that mean? Well, this detector is designed to have a hole in it in that direction because it's got to let the protons come in so that they can collide with each other. So if the new particles come right back out along the beam direction, they're going to completely escape this detector. You're not going to see them because they're going in exactly the one place where the detector has no visibility, no capability. Okay? So to sort of try to seal that loophole, a number of us have created a new collaboration, a new effort to build a new detector that will basically cover that possibility. And that new group is called PHASER. It stands for Forward Search Experiment in this horribly tortured acronym way. Okay. This is how big we are right now. We would love to have more people, but we've got about 14 people right now. The acronym, if you're wondering, many of you figured it out, I think, an acronym recalls another marvelous instrument that harnessed highly collimated particles and was used to explore strange new worlds. So phaser with a PH, right, in Star Trek here. So that's the idea. But okay, so how does this work? How's this going to possibly help anything? Well, you can't just, put phaser right where the hole is because there was a hole there for a reason. You need to let the protons go through, right? But, okay, so if you go far enough down the beam line, that beam has to curve because eventually it's going to make a circle around the Geneva countryside. So here's what we do. Here's the interaction point where the protons collide. We go 1 football field, 2 football fields, 3 football fields, 4 football fields, and eventually that beam, that proton beam, is bent around with magnets so that it can make a big circle. So what we do is we put phaser right there where it starts bending. That won't get in the way of the proton beam, but new particles, which we're looking for, they just go straight. They don't care about the bending of your magnet. They're very weakly interacting. They just go plowing through, even going through rock, and they can conceivably go straight into our phaser detector. And so we put it right there. Turns out if you walk 5 football fields down from Atlas, there's actually a tunnel. So this is the LHC beam, 100 meters underground. This is where all the action is typically. This is where the protons are going back and forth. But off on the side, there's a little tunnel, which hasn't been used for like 20 years. And the point is that you can put phasor right in that tunnel, and it will be on the straight line from this interaction point. It turns out these particles are extremely concentrated in one direction, so you don't need a big detector to find them. This is our most recent design of the detector. These are various components I won't get into, but the important thing is here's a person. Okay, so this detector is 5 meters long. It fits between me and that piano, and should be very quick, relatively, to do, and very cheap to construct. Okay, so phasor is small and cheap and fast, if we can get it built, but there are still many more hurdles to pass. So unlike the other ones, which already have data, I want to be clear that this is a proposed experiment, but we're working hard on it. Fortunately, the most famous living physicists in the world are already on board. You might think this is an arrogant statement, but this is a fact. Here are the most famous living physicists, Leonard and Sheldon from the Big Bang Theory. If you go back to an episode in the fall of 2017 and look at their whiteboard, you see phasor right there. So they actually are interested in our project. Okay, so with that, let me summarize. So 95% of the universe is still completely unexplored. So we really live in a pretty exciting age of exploration. Large experiments, big science, are underway and have exciting prospects for discovering new kinds of particles, and we hope to possibly identify the dark matter. The new wrinkle I told you about, part 3 of this talk, was that there are now promising experiments that are relatively fast, small, and cheap. Fast, I mean they might take years instead of decades. Small, sort of tens of collaborators instead of thousands. And cheap, millions of dollars, but not billions of dollars. Now, I want to be clear. I mean, clearly in a talk like this, I skim over tons of details and tell sort of lies to get to the point. So you all understand that happens, right? But I want to make one very clear. I'm not saying that these small experiments are going to replace the large experiments, okay? In fact, the small experiments largely depend on the large experiments. Basically, I could go into details of this, but I won't. These were made possible by big science, by the insights we gained by doing the big science experiments. And they're just in some ways sort of a spin-off, just like the internet. You all know that the World Wide Web came from particle physics. MRIs, all sorts of interesting medical devices came from particle physics. Shrink wrap, the fact that your turkey at Thanksgiving is not spoiled, that comes from particle physics. All these things are spin-offs, and this is another one. Okay, so I'm not saying this replaces big science at all. But the point is that it's a new idea. It probes different ideas and possibilities, and it's possible that one of these cheap, small, and fast detectors could actually tell us about 25% of the universe. So that's pretty interesting, and there's a lot of interesting things to come, so hope you keep your eye out for it now. Thank you.
Thank you, Jonathan. That was awesome. Questions? We've already been involved, but
Maybe start in the front and work back. Yeah.
Yeah, what's in this phasor detector to detect? And what are we actually detecting with it?
Yeah, so what the idea would be is that this new particle streams down 500 meters and then gets over to phasor, so it gets in here, and then it decays into positrons and electrons. So what we would look for is charged particle tracks in this detector.
So how does that relate to the dark matter, I guess?
Okay. So that particle that we would find possibly in phasor actually can't be the dark matter because it's decaying. So it can't obviously be, it's not stable on 13 billion year scales. But it quite possibly could be linked to the dark matter. It could, for example, decay to dark matter sometimes. It could be in a sector, what we call a sector of particle physics, which has the dark matter in it. So it sort of be, the way I would like to think about it is it might be the tip of the iceberg. The dark matter might be under the surface, but it would be the tip of the iceberg that might be leading us to dark matter. Yes?
If there are light particles bouncing around or moving around, messing with electrons, pushing electrons around, would this have shown up in traditional optical spectroscopy years ago?
So yeah, you have to go through all the tons of data that you might have thought would be sensitive to that. And the answer is that you always get out of those constraints because this particle is so weakly interacting. So its effects on all these observables you might have thought should have seen it is diminished like by many, many orders of magnitude because of the coupling that we're assuming. So it's just weakly interacting. Yes?
Oh, what theory or theories lead you to expect a light but weakly interacting particle?
Okay. So this basically comes out of sort of a big development that kind of crept up on us slowly, which is this generalization of dark matter to what are called dark sectors. So if you went back, even 15, 10 years ago, and you asked people about dark matter, they were typically thinking it was one thing, like one kind of particle. But as we move forward, and admittedly, as we didn't find it, we started having to think more outside the box. People realized, why should it be one particle? The known particles, there's tons of them, right? So why should this dark thing be just one particle? So maybe it's dark sectors. Basically, it's got different kinds of forces, lots of different matter particles in this dark sector. And when you start thinking that way, it turns out that you can have very natural theories where the particles have their own forces and their own masses, and they nevertheless have the sort of the same motivation for being 25% of the universe as our standard dark matter. So I'm skipping several steps here, but basically this idea that maybe dark matter might not be one monolithic entity has led us to a whole bunch of models where actually it can be light and weakly interacting. Yes?
If existing gravitational wave detectors were more sensitive or became more sensitive, would they be able to see light, dark matter, or is it so light that's an immediate contradiction?
Probably not. I mean, that's not the best way to look for these things. And these gravitational wave detectors are looking for enormous releases of energy that just happen to be in gravity waves. And because they're so enormous, we can see them. But I think dark matter typically is not going to be amenable to that sort of a probe. It's it's a mismatch of ideas, detector ideas, and the top particles. Yeah. Yes?
Going back to your spiral universe, how do you envision light and poorly interacting affecting these high mass objects, stars or whatever, in the tail?
Yeah, well, so, these particles are light, but no one told us how many of them there are. So to be 25% of the universe, if they're light, there's just a lot more of them. And so, and that's sufficient to allow them to have the same impact as, a heavy object, but one that there's fewer of. So it's basically the number density times the mass that gives you sort of the impact on these sort of gravitational things. And so this light thing is just simply assuming the particles are light, but there's a very large number of them. Yes?
Wasn't there recently a neutrino event at the ice cube experiment, and what did we learn from it?
Yeah, so there was, the exciting thing about ice cube is that they detect neutrinos all the time. But what we learned is that those neutrinos very likely come from a particularly well-known astrophysical object called a blazar. And so this is something that's called multi-messenger astronomy, where you sort of correlate seeing things in different channels. And it's very hot off the press, but one thing we possibly learned from it is where these extremely high energy cosmic rays comes from. That's a whole nother topic, but also something that I love and have dear to my heart. There are particles that, a single fundamental particle, probably a proton or iron nucleus, hit the atmosphere with the same energy as Major League Baseball, which is, of course, lots of particles. But that entire energy, a Nolan Ryan baseball is packed into one little particle. That's an incredible thing. And we don't really know where those come from. And this new ice cube observation may be sort of hinting toward an explanation of that. Thank you so much.